this is a study, the Yellowstone grizzly bear investigations from 2011. And see if I can move this thing a bit. We can do this. So, okay, there's a little grizzly bear climbing up a tree. And inside here is some data. There we go. Oops. Too far. Too far. Too soon. So this is a number of confirmed insect aggregation sites in greater Yellowstone ecosystem annually, the number used by bears. So bears do eat insects. And so what we're looking at is this data here. So the year and the confirmed number of moth sites. Okay, and what we want to do is look at this over time, create a model for it, okay, and then see if we can do some sort of analysis on the model, right? So this could be a set of data that was collected from 1986 until 1986 until like 2011. Okay, so there it is there. So if we're going to do a regression on something like this, we really don't want to use 1986, 1987, and so on. We really want to start with 1986 as being year zero. So okay, I'm just going to scroll up in this. So this data for the year, so in L1, the list, right, which is time, and generally time runs along the x-axis. Say at year 0, there were 4 moth sites. At year 10, which would be 1996, you can see there's 26 moth sites, and so on. So I entered all of these into my calculator, into the calculator. So let's do a scatter plot. So what we're going to look at is, so this is year 1986, that's 10, 20, 21, 22, 23, 24, 25, so 25 years worth of data, okay? So for our window, we're going to say, let's go from 0 to, and I'm going to go to 30. So 30 would take it out to like 2016, right? If we were doing what? So if I'm doing data past 2011, what's that called? Extrapolating, okay? We would extrapolate. So I'm going out. And then number of moth sites goes up to 37. So we'll go from 0. Oh, sorry, that's X scale. So that should always be 1. We'll go from 0. Let's go to, say, 45. We'll go by 5s. And I just want to look at the scatter plot. So I go second y equals. I turn on the stat plot. Just turn that on and hit graph. So there's the data. So does it look linear? Does that look like a straight line? No, not really, right? So let's say these numbers look a little off. So they should all be like 37. I'm going to go in and look at the data, make sure that the last bunch are all 37s there. Yeah, okay, they are. So what could it be? It could be quadratic, right? So let's try fitting a quadratic to this. So we're going to go stat and over to calc. Number 5 is a quadratic regression. Okay, I'm going to put the regression equation into y1. Hit calculate. Okay. It's going to work out the equation. We're not interested in that so much right now, right? We're interested in, hey, let's graph this, see, does that look like a quadratic? So does the curve fit? So what do you say? Curve fit? Looks pretty good. Okay? So that could be quadratic. Okay? So let's go a little bit more into the future. We went to like 2016. Let's go out to like 2021 or something. As a matter of fact, let's go another 10 years past that. Let's go to 40. See what happens. Where it's recording, maybe it's picking you up, maybe it's not. I don't know. So what would we have to say if we were going to say this was quadratic? What would we want to say? Probably want to say, hey, this could be quadratic, but we're going to have to collect another few more years worth of data, right? Like, let's run the study for another 10 years, see what happens. And if the data starts to come down along this line here, then we can say, quadratic may be a good model for what we're looking at here. But we've also seen graphs that do this and then climb. What kind of graphs kind of do this but then climb up? So those are cubics. So we can go to number 6. We can run a cubic regression. We're going to want to do the same thing. We're going to put the regression equation into y1. Okay, we're going to calculate it. We're not worried about the equation right now. It's going to give it to us. We could write it down, but we just want to say, all right, let's graph it. See if that looks. Could this be cubic? Well, the cubic looks a lot like the quadratic. So, yeah, it could be cubic. And then maybe at some time in the future, this thing's going to start climbing back up again, right? That's a possibility. Okay, so if we were analyzing this data for somebody, then we'd say, well, we really don't have enough, right? We've seen this, and we just kind of wonder if it keeps going down, it's quadratic. Maybe it's cubic if it keeps going down. I wonder about these guys here. It looks like there's, I can trace over it. Like there's 537s, and then I seem to have some more numbers here. I'm gonna go look in the table. No, okay, weird. All right, so it's just something to keep in mind, right? We're looking at data. It's not linear, right? It's not a straight line. Could be quadratic, could be cubic, and the thing that we would probably say is, we're going to have to study this for a few more years to look and see what's happening to try and figure out what kind of equation this is. Okay, so let's go to, not that, this. Here we go. All right, modeling data with a curve of best fit. So this is your worksheet. So a curve of best fit is a curve that best approximates the trend in the scatter plot. For us in this course, it will either be quadratic or cubic. On any assessment, so on the test or on the diploma, they will always tell you what to run. Okay, so if they say determine the line of best fit, that's linear, right? Otherwise, they'll say run a quadratic regression or a cubic regression. So, Damien's physics class measured the height of a bouncing ball in the school gym. The ball was repeatedly dropped from the same height. The height was recorded every 0.2 seconds with a special camera starting at the first bounce. 3 trials were performed. All the data is listed above. Enter the data in your calculator and plot the data. Okay, so I'm going to pause this because... Okay, so while you were away, so we filled in the X values, the time in L1, so, and all 3 charts, so 0, 0.2, 0.4, 0.6, 0.81, 3 times, and then we put the heights into L2. Plot the data. Okay, so we need a window. So this ball is going from 0 to 1 second, so 0 to 1 by 0.2. And the y values are 0. Let's go from 0 to 3. To 3, we'll do that by 0.5. I'm just going to go to y equals because I want to clear out what's in there. My scatter plot is on, so if you look up at the top and plot 1 is dark, is bolded, then that means that your scatter plot is on. If yours isn't, just go second function y equals. Go into plot 1 and turn it on. Okay, then hit graph. So we should all see a scatter plot that looks pretty similar to this.
When you want to turn on plot one y equals, you have to go and do that.
It works great. You can do it.
Well, I just don't know if that changes.
No, as long as you turn it on. I think you can arrow off the plot and just hit enter. Yeah. Which for us would be easier because we don't actually change anything. I'm just sort of used to going in because then you get the option with all the menus, right? But for you guys, yeah, for us, as far as any of this goes, looking at scatter plot, you just arrow up plot one, hit enter, start. Everything else, just the default is fine. So you see it's a little fuzzy because there's 3 data entries for each of these guys. Okay, what does it look like? A nice straight line will fit that? We'll just draw a line like that? No. So what kind of regression are we going to run? Quadratic. So we'll go to stat, we go over to calc. So number 5 is quadratic regression. So either you see the word quadrag and then you're going to put the y1 in and hit enter and it'll run it, or you see a screen that looks like this. Go down to store regression equation and you can go vars over to y vars, so that this will work for every calculator. Over to y variables, hit y1, hit enter, and then calculate. Okay. So it runs the quadratic regression and it gives us this. And then here it says round the values to the nearest 100. Okay, so I should figure out what I did with the whiteboard pen. Okay, found it. So we are going to enter the equation. Y is equal to negative 9.79 x squared plus 10.01 x plus 0. See, now it says 100, but if you look at the c, it's 7.14 e to the negative 4. So c is 7.14 times 10 to the negative 4, which is 0.0071430. So round it to the nearest 100, that's just a 0. So watch out for if you see that negative e to the 4. So we don't really need to enter that. We can just enter this. That's our equation. How good is it? Let's hit graph. How does it look? Pretty good. So there's a thing on the calculator that will tell you how close. We used to do it. We don't do it anymore. It's the r squared value. It tells you how well the curve fits. It's not something that we have to worry about. If you do have to worry about it in post-secondary or something, they'll show you how that works. Or you can go online and look up how it works. It's not something we ever have to do because they'll just say run a quadratic regression on a question like this. Okay, so when you write out the equation, make sure that you're rounding correctly. Sometimes it may say 2 decimals, 100th is 2 decimals, 10th is 1, 1000th is 3, or it'll just say 3 decimals. Graph the function with your scatter plot. Yeah, so we did that. Use the graph to find the height of the ball at 0.7 seconds. So this is an x value. So on the calculator, we go second function calc, value number 1, x value 0.7, hit enter, and it tells us that the y value will be 2.21. 2.21. Units on this thing? Probably meters. Okay. Meters. Use the equation to calculate the height of the ball in 0.7 seconds. So if we're using this equation, we'll go y is equal to negative 9.79 times 0.7 squared plus 10.01 times 0.7. So do you think we're going to get the exact same value? Well, one way to find out, times 0.7, okay, that's not the right way, 9.79 times 0.7 squared plus 10.01 times 0.7. And I do not have a plus in there, so hang on. Bring that back down and insert a plus sign. And 11 point, doesn't, 0.7. 9.79, yeah. Oh, negative 9.7. That'd make a difference, wouldn't it? Let's go insert that negative, yeah. Second insert. All right, 2.21. Okay, so it did come out same value. So it may differ, especially 2.21. It may differ. It should be reasonably close, right? Should be reasonably close. Or if you don't put the negative in, it's just way off. Then you're confused. And there it is out on the internet. Well, this guy doesn't know what it is. Use the graph of the function to find the time. So the time is x, at which the height, so the height is y. So for this, we go to y equals. And we say, leave y1. I want to put in a height of 1.5. And I want to graph that. And I want to know at what time. So what is the x value? So we're looking for the x value of both of these points. So it'll be at 1.5 meters twice, right? If we're bouncing the ball or launching the ball or whatever's going on. On its way up, it's going to go through 1.5 and on its way down. So we go second calc. So these are intersects. And we just move to about the point of intersection. You can just actually hold that key down. I can't. Hit enter 3 times. So we get 0.18 seconds. And intersect again. Now I don't want to go all the way around here. I'm going to go on the red line. So see it's on the blue. If we down arrow, it'll take it to the red line. And then I can just move across. So I can just toggle that on. And we can just move. You just hold it down. I'm doing the virtual equivalent. Okay, so move to the point of intersection, hit enter 3 times. And what it's doing is going from the red curve to the blue curve, and it's got a guess, and we get 0.84. Okay, again, rounded to the nearest 100, 0.84 seconds. Okay, so once on the way up, once on the way down. And it looks like the next one is asking for the maximum height and the time that this occurred. So we're going to do a second calc of the maximum, which is number 4. So to do a max, you move up to the left of the maximum point. And hit enter, you go to the right of the maximum point. So just go up over top and come back down a bit, hit enter. And then for the guess, you just move to about the maximum point and hit enter. So we will have, there will be a maximum height of, so height is a y value, 2.56 meters at, and time is the x value, so 0.51 seconds. So, and what time this occurred. So maximum height of 2.56 meters at a time of 0.5. So make sure there's units on there, 2.56 meters, this is seconds. So if we're doing something with the context, then we should put units on. Consider the data in the table. Make a scatter plot of this data. So we're just going to enter this data into our calculator. So one more time. Actually, what I'm going to do is go to y equals first and just clear out everything that's in y equals. Okay, that way we won't get confused. Because if you just look at the scatter plot, but you've left something in y1, it'll throw the curve on top. Let's clear. So second mem, number 4 is clear all lists. Go to stat, edit, and oh, that's small. So 0, 5, 10. So from 0 to 50 by 5s in L1. So you have to arrow over to L1. Okay, I'm just going to pause. We'll enter that in L1, the other numbers in L2. So let's go get a window for this. So our x values, which are in L1, go from 0 to 50. So we'll go by 5s. Now, I don't know if we're going to do any extrapolation, but I mean, if we are, we'll just have to reset the window. And y values seem to start, go up to 102. So let's go from 0 to like 120 maybe. And scale of tens. If your stat plot is still on, then when you hit graph, you'll see the stat. You'll see the points. So that's a nice straight line, right? No, it's a nice parabola. No, what is it? It's a cubic. Okay, looks like a cube. So remember, on the test, on the diploma, you will be told to run a cubic regression, right? Or linear, or quadratic, or whatever. All right, so this looks like a cubic. So stat over to calc. Number 6, cubic regression, right? I mean, it's all the same at this point. Okay, so by now, and you have to use your calculator, so however yours, whatever yours shows. Alpha F4 enter is the way to get a Y1. It's a different way to get a Y1. You've got a newer calculator, right? Otherwise, vars, Y bars, enter. And then hit calculate. And it'll get you the equation. So cubic. Oh, this said do the linear. Nah, never mind. So cubic. So if we're going to round to 2 decimal places, I'd actually go to 3 in this case because we do have a cubic. So it's negative 0.002 x cubed. Right? Rounding to 2, you'll end up with 0x cubed. It's like, no, we know this isn't 0x cubed, right? We can see that it's a cubic. Plus, let's go 0.178x squared minus 5.275x plus 121.301. So in this case, I'm going to 3 decimals, and we didn't run the linear because we could look at it and say, hey, that's not a linear. All right, so okay. Skip down to here. All right. Cubic. Got that. Graph this function. Use it to find the value of x when y is equal to 90. Okay, so if you want to find a y value given an x, you use second function calc value. If you're given a y value, you go in, you plot the y value in y2. Okay, then you graph. Okay, so this time the graph, it's going to draw the cubic on, right? Because we said put it into y1. We can see that as far as the cubic goes, that graph fits very nicely to the curve. And to get the x value, second function calc, and number 5 is intersect. So we just got to move to the point of intersection. And then it's asking first curve, so it's on the blue, it's on the cubic. Second curve, it'll jump to the red. It's not going to go anywhere because we're on that spot, really. And then guess, and we get the value. So 7.76. 7.76. So we don't have any units with it, right? We're just given this table of numbers. It's not like one is in meters and one is in seconds. You know, one of the things we did the first day with the gas price, it's not like it's price per liter or anything like that. It's just a table of numbers on which we ran a cubic regression. Okay, what would be a better fit? The one that actually hits it, which is cubic. So cubic. Part C. A golf club manufacturer carrying out research on hybrid irons recorded the path of a golf ball from tee to green on a par 3 hole. The height h in meters of each golf ball was measured every 0.7 seconds after being hit. That's your time, t. A scatter plot was created and a curve of best fit was found using the regression function in the calculator. Okay, so this is like the Yellowstone bear study data. We entered the data, we ran the regression. Here's the equation. Using this equation and your graphing display calculator to answer the following questions, round answers to the nearest tens where necessary. Okay, so we are given an equation. So I'm just going to reset the calc. Second mem 7, left arrow, enter 2. Right, that gets rid of everything. Then the table's gone. Anything that was in y equals is gone. And I can just start clean. Okay, now for you, it's going to take a little while to clear the calculator. It doesn't happen immediately. But then we go in and go 4.90. So we can't use t's. Okay, we have to use x's. Plus 25. You don't really need the zeros. It won't actually do anything with them. Plus 0.03. And we need, well, I don't know what the time and the height and that. We're going to have to come up with a window. So let's just take a look. Determine the height of the ball, how long it took for the ball to hit the ground. Okay, so what I'm going to do is go look in the table. So as far as hitting a golf ball goes, we're going to start at time 0. It's going to go up in the air. We're going to let it go until it hits the ground, and we can see that if that's a golf ball. I got something wrong here. Oh, forgot the negative again. It's like, wow, it's at 700 meters high. All right, let's go look at the table. Okay, all right, so it looks like if we go to 6, right, we're going to hit the ground somewhere between 5 and 6. The 0.03 centimeters at 0 seconds would be the height of the ball on the tee, right? It'd be sitting on a tee, so 3 centimeters off the ground. That's why your height, instead of being 0, it's not lying on the ground. It's a ball from tee. Okay, so, and how high? 30, we'll go say to 35. So window, we'll go from 0 to 6 by 1s, and from 0 to 35 by 5s. And let's hit graph. So we don't see any points because we didn't enter the point, right? So somebody else entered the point, somebody else ran, they got this equation. We're just going to basically run with the equation now, use the equation. So determine the height of the golf ball above the ground after 3 seconds. So this is time, and time is your x value. So second function calc, number 1 is value, put in 3 seconds, and we get a height of 30.93 meters. Determine how long it took for the ball to hit the ground. So the ball hits the ground when its height is 0. So what I'm going to do, actually, I like to do instead is going to y equals, I'm going to put y2 is 0. Now, you could just do a 0. You can use the 0 function of the calculator. I like to do intersect better, so I'm looking for the intersection of the blue and the red line. So if you don't have a color calculator, you're not going to see the red line, right? It's just going to draw a line right along the x-axis. But it'll be there, and we can use it for an intersect. So second calc intersect, and then I'm just going to move down. So you actually have to hold your button down. And move down to about the point of intersection there and hit enter 3 times. And we get a time of 5.10, so 5.10 seconds is when the ball hits the ground. Last question. Determine the times the golf ball was 20 meters above the ground. Okay, so 20 meters is a height. Height is y, the y value. So instead of 0 here, we're going to put 20. And graph that. So here's our graph. So y values, you go into y2. Your equation is always going to be in y1. Just the way. Equation is going to be in y1, and your other height, we're putting another height that goes in y2. What time? So notice 2 times, right? Because it reached a maximum height of like 30 something. So it's got to go through 20 meters on its way up. So we're going to do an intersect. I'm just going to move down to the red line so it's faster to go on the red line. And 1, 2, 3. So 0.99 seconds. Basically 1 second. But if it asks for the nearest hundredth, it would be 0.99 seconds. And we're going to do intersect again. And this time, well, I'm not really doing any of the work, so I can move along the blue curve. No, now I have to do some more. Up to the point of intersection. So you can see it's around 4. So 4.11 seconds. So 0.99 seconds after the ball is hit, it will reach a height of 20 meters. It'll continue going up, and then at a time of 4.11 seconds, it will be coming down and will also reach a height of 20 meters. So there are 2 times. Okay, maximum height and the time that it took. So we want the max. Second count. And we want number 4, we want the maximum. So to do a maximum, you have to go to the left. I'm just going to let this go to the left. And then you have to go to the right. No, wait, it's on left bound, so hit enter. Then move over to the right. So just go beyond the maximum, right? I mean, start a little before, then go a little bit further, and then to the middle. And we get a maximum height of 31.92 meters at 2.55 seconds. Okay, so behind you roundy, it goes up about 32 meters high after about 2.5 seconds. Any questions? Okay, so that's curve of best fit, right? On the test, you'll be told what